Welcome you all to this cryo-EM course. Last class we already discussed about what is the main component for cryo-EM sample preparation. Especially what do we need? We already discussed for cryo-EM sample preparation we need liquid nitrogen, we need liquid ethane, and then we also need glow discharge grid. And I also discussed that glow discharge grid generally we are using from the company made by Quantifoil or C-Flat. Sometime we can use the homemade holy carbon grid. Those kinds of grids are called the holy carbon grid, what I mentioned in the last class. So if I just consider, so last class what I discussed with you guys that okay, so if we have a square something like that, and then this is our grids, and now this individual square, if I just go to a enlarge view, what we have holes, and those holes has a uniform diameter, all may be either 2 micrometer or 1.2 micrometer or 0.6 micrometer hole size, and then there are also a fixed distance between those two holes that will really help us for automatic data collection. These kinds of grids are called the holy carbon grid. Holy carbon grids. So whatever I told last class, there are different types of holy carbon grids are possible. So those grids will be either 2 by 2 or 2 by 2 or something are 1.2, 1.3, or this number may be changed, only that hole size and distance between hole we have to pay attention. So whenever we will freeze cryo sample, we always remember that we want to use holy carbon grid, not continuous carbon grid. In continuous carbon grid, those hole will be not there, this hole will be covered by amorphous carbon, and then there will be a formovar coating. So in this particular case, holy carbon grid is very important whenever we will do normal cryo-EM freezing. And now in this holy carbon grid, sometime we have to cover some kind of carbon layer or graphene oxide that will really help us. More sample can bind. So graphene or graphene oxide related grids that we will discuss in the later stage during our advanced sample preparation topic. But in this particular case, sometime if you look at, so what I showed you here, that we have a square where we have those holes, uniform sizes hole, and then there is a distance between that hole. Now if we look at those hole and we want to coat with a amorphous carbon, there will be a very thin layer of amorphous carbon on top of the entire area. So those thickness of this carbon layer, it will be very thin, and then in some protein, sometime that ribosome or some kind of bacterial toxin, they will attach more when you have a carbon layer. So carbon layer is also here, but this carbon layer is very thick than this carbon layer. This amorphous carbon layer on top of this holy carbon grid is very thin, so it will not give a very strong background. That is the reason sometimes we have to take this kind of holy carbon grid, and then we have to coat this grid with carbon, or commercially those carbon coated holy carbon grids are also possible for special purposes like ribosome or some kind of very large complex which cannot stay inside that hole. We can use this kind of grid for cryo freezing. So this thing is called carbon coated holy carbon grid. So carbon coated holy carbon grid we are using for a special purposes, mostly for cryo-EM freezing we are using holy carbon grid. So there is a difference between these three. So one, it will say continuous carbon for room temperature or negative staining temp. then it is the next one, it is called holy carbon grid, and then next one it is called carbon coated holy carbon grid. So we have different types of sample preparation grids, and that we can use it whenever it is required. Whenever we will prepare our sample, sometime different grids we have to also optimize. Also you have to remember, whenever we are using different types of grid, that continuous carbon coated grid or holy carbon grid or carbon coated holy carbon grid or graphene coated grid, all the cases how much glow discharge you have to do, there is no specific number that you can use this number, this many seconds you have to use it. So sometime you have to optimize those things. So those grids, whenever you will change any grids, it is better to optimize those parameter and then start freezing your sample. Sometime we are using those grids are mostly copper, the outer boundary and those metal bar all will be the copper made. Sometime we are using the gold grid also, so either we will coat with a gold or mainly the gold grid we can also use it. Sometime that gold grid is very helpful because deviation between that carbon layer and this metal, it will be different and it will be much more giving the very good signal when we are using gold grid. Some protein we can see it is really helping if we use the gold grid, but most of the time we are using this copper and then normal holy carbon grid. Now let's see how we are freezing our sample using the holy carbon grids. If we come here, this is the entire protocol of cryo-EM freezing. This entire process, how we are freezing our sample, that will be very much clear when you look the video in the later stage. So we have a practical session where we demonstrated how to use Vitrobot to freeze the sample. So there are different types of freezing units are there. Those are so previously we are using the manual plunger where we have to blot our sample manually, but in the recent days there are plunge freezing instrument from the Gatan, from Thermo Fisher and from Leica also. So what we are doing, first let's discuss about that one and then we will discuss about the different types of freezing instrument. Here this is the most common technique we are using for cryo-EM sample preparation. Now first you look at this one, this is I told you that cryo-EM grid. This cryo-EM grid, what do we have in this cryo-EM grid? In this cryo-EM grid you can see there is a thick boundary area, that is the area we can use it to pick up the grids from the petri dishes and then tweezer can hold that area. So we never want to touch the tweezer somewhere middle of the grid because that will break the carbon layer. Not only that, it will bend the grid. If it will bend the grid, so that eccentric height it will change. During the imaging it will create lots of problem. Now this is a very flat grid. So if you just come here, you can see this is the enlarged view of this grid and this is an SEM image, and the many places you can see there are some broken carbon areas. So I intentionally selected this grid so I can even show you at higher magnification. Same grid, if you look at, you can see some area there is a continuous carbon layer, some area there is a broken carbon layer, and so wherever you have a continuous carbon layer, that will give you a very smooth background, and where you have the holes inside that. So here if you look at this one, so those are the squares we are looking here. So individual small squares we are talking about. So based on that, I already discussed that grid will be 400 mesh, 300 mesh or 200 mesh grids. So based on that, how many squares are there, based on that we are mentioning that is it a 300 mesh grid or a 400 mesh grid. Now if you look at one particular squares of this one particular square of this grid. What you can see in these squares, you can see that enlarged view here. There are some intact carbon layer, we can see it here, and some broken areas is here. So definitely this grid is not well handled. So most of the time we want that carbon layer will be intact, there is no damage in the carbon layer. Now if you pay attention to one of these squares here, what you can see here in this particular square. So if we just pay attention to one small square here, you can see it that in this particular one small square, if you go inside, there is a uniform sizes hole. Uniform sizes hole means the diameter of this hole is fixed and the distance between this hole is also fixed. Now you can see that it is a uniformly distributed, all these holes. Now this is the overall architecture of this grid at different magnification. Now if you come here, what we are doing, this grid, we are taking it with a tweezer. Tweezer is holding outer part of this grid, and now this is the tweezer which is holding that grid, and this is the pipette where we are using this pipette tip to add a small amount of sample here. How small is the sample amount? The sample amount will be only 3 microliter, because if you increase the sample volume and if you decrease the sample volume, when you will blot the sample, your blotting parameter, it will change. Now if you look at here, we are just adding a small amount sample, and then this sample will spread all over the grid. Why it will spread all over the grid? Because grid is already glow discharge. Now here this is, you can see one part of this freezing instrument where you can see there is a 2 blotting pad is there, where we have a filter paper and there is a small amount of sample is attached here. So this 2 blot paper, it will come closer and blot this extra buffer solution. So now you can see in the next step what is happening. The small amount sample, both the blotting pad comes closer and attached with the grid. So here you can see both the blotting pad are very close to each other and it blotted the extra solution from here, and then quickly plunged this one into the liquid ethane. So here you can see there is a container where the outside of that container will be liquid ethane, liquid nitrogen, and inside there will be liquid ethane. Liquid ethane temperature will be minus 180 degree centigrade, and when we blot this sample, we quickly plunged into liquid ethane. Now here you can see this is one window, and this instrument is called the Vitrobot Mark IV, and if you look at this window, there are lots of parameters you can adjust, where this is the blotting area where there is a 2 blotting pad is connected here and your grid will stay somewhere here. Now within this chamber you can control the temperature, you can control the humidity, you can also control how much blot force do you want when it is going to blot your sample. Not only that, how long you are going to blot your sample, that you can also control here. And when the blotting is done, then you will quickly plunge into liquid ethane. Now if you come to this particular area, what is happening, you have a uniform sizes hole everywhere, and then there is a exact they are separated with a particular distance, all this hole. Now whenever you added any buffer or solution, so some of these small amount solutions stay inside this hole, and when you are blotting, most of the water or buffer, whatever is there on top of the carbon, it will absorb by the filter paper. But inside the hole, due to the surface tension, a small amount of sample will stay inside there. Now if you just consider this entire grid quickly plunged into liquid ethane here, what will happen? So whatever the small amount sample is there inside that hole, liquid ethane, the specific heat is very high, it will absorb the heat very fast from that solution. When the heat will absorb from this hole very rapidly, it will form a amorphous ice inside this hole, and the sample will embedded at different orientation. So if you look at this, same square after freezing, you can see the intensity is changed. In this particular hole, if you look at this one, the intensity is much stronger because this is only a holy carbon grid. We didn't add any sample. When we added sample and after freezing, you can see overall intensity is changed, and within this hole it is not as white as this one. This one is little bit gray color. So here there is no ice formation when the overall intensity is very high. Here there is a ice formation. So now we have to target this individual hole for the imaging. So what it is happening, there is a solution on top of your grid, and then we are blotting the extra buffer solution will go away, and then this small amount sample where protein is oriented at different orientation. So it will be not a single orientation because everything is in solution in this particular hole, and then when we are quickly plunged into liquid ethane, everything is fixed. So this is the technique. Basically we are adding sample and we are fixing the sample in the amorphous ice. That is one of the reason in this cryo-EM sample will stay at physiological condition. So sample cannot move anymore, and due to this very low temperature, it will maintain all its physiological behavior or overall architecture. That is one of the reason we are using cryo-EM for structure determination, or if we want to study the morphology of any cell, it is better to use cryo-EM for that study. So now next it is coming that when we have that cryo sample or cryo grids are ready. So in this particular case we already freezed our sample, our cryo grids are ready. So this cryo grid generally will stored in liquid nitrogen in 24/7. It should not come out from the liquid nitrogen, because if it will come out from the liquid nitrogen, if it will exposed with normal layer and temperature, this amorphous ice will melt immediately, and that will damage the sample quality, and that will form cubic ice or crystalline ice. That is the reason we have to maintain the temperature below -175 all the time when you will freeze the sample, and we try to keep that temperature. So if there is a gradually temperature will increase, you can see different kind of ice pattern also, or when you are handling those cryo freezing, if you are not handling this entire system properly, there is a chance there will be a lot of ice contamination, or your ice will start melting, or different kind of ice contamination you will get it. That I will show you in some images that what kind of ice contamination you can get it. So but take home message is that whenever you will freeze your sample, you have to be extra careful. You cannot handle this container. So whenever you will handle this entire process, you have to be very careful. Your and your grid will always stay either in liquid ethane or in liquid nitrogen. It should not exposed in normal air. Now what is next? Oh, we already have a grid, and now you consider that grid we inserted in electron microscope. So if you just recall that electron microscope, we are using a normal cryo holder, or sometime we are using a cassette. Within that cassette we have total 12 grids, and then cassette will be inside the microscope in autoloader, and from that autoloader single grid it will go inside the microscope, and then you can check those grid and screen. When you are screening those grids, you can see this is one of the grid square we are looking at. So I will come back to that particular part when you will image a grid at a different magnification, what you will see. So here you just consider this is one of my grid, and now this is, I already told, sample is inside this particular hole and it is in a fixed condition, it cannot move anymore. So sample cannot rotate. So this is basically completely fixed. Now if I go to the next one, what we can see? So this is, you consider that this is an amorphous ice inside that hole. If you look at inside that hole, we can see this amorphous ice. Now the individual protein molecules which all have a 3D structure, they are oriented at a different angle. So different orientation you can see. So we are always expecting protein will has a different orientation when we will freeze the sample, but that is not the true case for all the sample. There will be some kind of deviation, and that we will discuss in the later stage. Now in this particular case, you look at that, okay, there is amorphous ice and protein is embedded at different orientation. So you just consider that we are baking a cake at the initially, this is the layer, that liquid layer, then we are putting some kind of nuts, and then when it is baking, it has a different orientation within that. So it will be not a fixed orientation anymore. So here we are expecting the same thing. Now when electron beam will pass through this sample, what we will get? So this is a transmitted electron beam. So entire thing will transmit, and then it will give us a 2D image of this 3D object. So if I look at this one, we can see a 2D image of some 3D objects, and those in this particular case you can see those are our protein molecules we are looking here. So these black molecules are the protein molecules here. So when we have this one, basically that will help us to take those images and do the image processing. Now the similar thing again, that okay, we have this one has a different orientation, electron beam will go through that sample and will get a 2D image. Here we are getting an 2D image here. And the other hand, so some cases that we already discussed about the liposome. What is the liposome? Liposome is a lipid bilayer. So we are making those kind of liposome in our laboratory, or maybe any cell, if you just consider, it will be always a 2 lipid bilayer, it will be there. So here we are in the laboratory, we are just using different types of lipid, that phosphatidylcholine, phosphatidylserine, and then long chain carbon, that is the C18, C16, that is the long chain, and then we are using these things in the laboratory, and there is a particular process where we can make the liposome. Then when we will make the liposome, it will make a spherical shape of this. Now if you just consider liposome and the protein molecules, then definitely liposome sizes are much higher or bigger than our protein sample. So generally liposome size minimum you can make it 100 nanometer, 200 nanometer, and you can make much bigger size also. Sometimes that liposome it will fuse with each other and then make a very large vesicle kind of thing. But if you just consider about the size of the protein, it will be only 5 nanometer or 8 nanometer, something like that. So if you just compare, the sizes are very the size of the protein is much smaller than the liposome. Now when you are freezing this liposome sample, you can see this is a similar kind of hole. So this is the hole what we enlarged, and we are showing it here, where you can see different kind of liposome, and those circular things are the liposome. Now here you can see that some cases that liposome is concentrated near the carbon area. So now I will just revisit these things, that okay, this is the carbon layer, actual carbon layer, this is the actual hole. Inside that hole we have our sample, and then we are trying to image these things at little bit higher magnification. This one, if I just consider, magnification will be 380x magnification, and this one if we just consider, it will be 4200x magnification. Now in this particular magnification you can see this is the entire hole at the enlarged view, and those are the liposome which are distributed. Now I cannot tell this is uniformly distributed. So sometime I have a feeling that okay, many of these liposome are very close to the carbon. Why they are close to the carbon, that we will discuss in the later slide. But you can see one problem here. So you can see there is a lot of similar liposome kind of things are attached on the carbon area. So liposome is not staying inside the hole, liposome is moved and it is located near this carbon area in those region. And that is, I was telling that there are some protein or some biological macromolecules, they have some affinity towards the carbon and they move towards the carbon. Sometime we have to protect that one, and then we can play around with our glow discharge parameters, or we can coat those holes with a very thin amorphous carbon and then we can add the sample. There are some drawbacks also to doing that process, but that is another way to avoid that sample will go away from the hole. Now if you look at the next one, this is another condition where you can see that okay, liposomes are distributed near all over the hole. It is not very uniform but better than this particular hole. But if you look at this one is looking very nice because entire hole is different types of circular liposome. You can see there are different liposome and it is uniformly distributed. I am not talking about the size of the liposome is uniform. Those, if I just consider those individual particles are one biological macromolecules, those macromolecules are distributed uniformly inside this hole. Now if I just pay attention to one small section of this hole, because we cannot image this entire hole because the overall diameter of this hole will be either 2.2 micrometer or 1.2 micrometer. So our sensor is only this big, and so we are targeting one particular area of this hole and then we are imaging. And if you look at this is basically 45K magnification. In this 45K magnification you can see those individual liposome here, and you can see both the layers are clearly visible here. And you can see here also there are many liposomes are attached on the carbon, but there is a lots of background is here. So if you pay attention here, there is a lot of spike things are there which is making this surface of the liposome very ununiform. So it is not uniform at all. So here you can see the outer surface is very smooth and very uniform. So that is one of the reason for the small protein also, when this small protein moves towards this carbon, we don't want to target imaging in those particular areas. So whenever the small protein or any biological molecule stay this carbon area, generally we don't want to image those. So always remember that any sample in this region, it will not give you a very good result. So better always when you will image, we will target this particular area for the imaging. Okay, so what is the next final step here? When we are getting our data, so we are talking about this is our data, this is a 2D image. You can see I already told you those black molecules, this is this black pattern here, this black patterns here. So it will be much easier if I just show it using the pen. So here you can see those are the small particle here. So individual protein molecules, those are all individual protein molecules that we are interested about. So here there are many all over the grid, we have a many particles like that. Now if we just go to the next step, what we are doing, we are calculating the 2D averages of those raw particles. Okay, So we have a similar kind of particle together, we are putting them together and we are calculating a 2D averages. We will come back and discuss about what is 2D averages. Here you can just consider that 2D averages we are calculating where we are trying to increase the signal to noise ratio. So this is called signal to noise ratio. This signal to noise ratio we are trying to increase, and that is the reason same orientation particle we are keeping it together and then we are calculating their averages. When we have these averages, so those are the averages from this raw particle. If you look at this raw particle, it will be not very clear about their shape, but if you just calculate their average, the contrast is so good, you can see lot of fine details inside those molecules. So you can see there is a lot of details you can see. So this lot of details basically either alpha helix or beta strand of your protein molecules. Now from this raw noisy data you can see all the details of your protein molecules. Now in the final stage you will back project all of them to calculate a 3D reconstruction, and we are getting our 3D reconstruction from this data. So this is the overall principle, that this is the part of the data processing or we can tell that 3D reconstruction. So that is the part we are going to discuss in the later stage, that what is 3D reconstruction and how we can calculate a 3D reconstruction from our raw particle, and that is the part where we are doing all this data processing. We will do it in the Fourier space. In that particular time your Fourier transform term it will come into the picture and it will help us to do the 3D reconstruction. Now if we just go to the next one, you can see that there are similar type of liposome. Here you can see there is a liposome, and then liposome is decorated with some kind of toxin molecules. And now here you can see this is the enlarged view of that sample. If you just go for a 2D average calculation, you can calculate a 2D averages from this raw particle, and finally you can approach in same way and get a high resolution 3D structure from that 2D averages. Those are the 2D averages, and we calculated those things from the raw particle. So this is the overall procedure how to use cryo data and calculate a high resolution 3-dimensional structure. But so this is the final stage that we can get a high resolution structure, but at this moment we are more interested to discuss about that how we can prepare our cryo grid and what we are looking for when we are screening those grids. So the next class we are going to discuss about how we can screen our sample and how we should collect our cryo-EM data, and then we will discuss about what is a good data, what is a bad data, and then finally we will come back and discuss about that 3D reconstruction from those data set. Thank you all for your attention.